Okay, welcome back. This is section 2.2, completing the square. We're going to talk about how to solve quadratic equations by completing the square. This is going to include using a method called completing the square to transform any quadratic equation that's defined in x into an equation of the form the quantity x minus p squared equals q that has the same solutions. We're also going to complete the square in a quadratic expression to reveal the maximum or minimum values of the function it defines. Okay, so let's start off by a little bit of algebra review. When we expand squared binomials, really the quantity x plus 1 squared means x plus 1 times x plus 1. And we learned in Algebra 1 that we then distribute or FOIL each of the terms individually. So x times x becomes x squared. X times 1 becomes plus x, 1 times x plus x, 1 times 1 plus 1. And we can combine like terms, so we get x squared plus 2x plus 1. And as we do more of these, we should start to notice some patterns. When we do x minus 1 times x minus 1, we know the first term has to be x squared, because x times x is x squared. And then we notice that when we multiply the middle two terms, they're always going to be like terms when we're squaring a binomial. So we have minus 1x is minus 2x. Negative 1 times negative 1 is plus 1. And as we continue going on, x plus 2 times x plus 2, we notice that the first term is always the square of this term, and the last term is always the square of the second term. So what about this middle term? Well, let's do one more. So we have x minus 3 times x minus 3, which is x squared. Now here we had plus 4x, here we have minus 2x, and here we have plus 2x. So let's look at the pattern. Here the second term is 1. Well, 1 times 1 is 1, so that gives us our last term. But 1 plus 1 is 2. Negative 1 minus 1 is negative 2. 2 plus 2 is 4. Negative 3 times negative 3 is negative 6. And in fact, if you take the second term, multiply it to the first term, and then by 2, you get this middle term here. So negative 3x minus negative 3x, or negative 3x times 2. And then the last term is always positive because we're squaring that term. So even if it's a negative term, it always becomes positive. And in fact, this holds true for any squared binomial. So the quantity x plus 4 squared becomes x squared plus 4 times x times 2, 8x, plus 16. 4 times 4 is 16. And x plus 5, quantity squared. Go ahead and pause the video, try that on your own. And you should get x squared plus 10x plus 25. So we notice that this middle term is always twice as much as this term, and the last term is always this last term squared, and that's going to be important to remember in a moment. Because all perfect square trinomial patterns come from this process. I can take this and go backwards because 6 divided by 2 is 3, and figure out this middle term, or the last term, 3 squared, is 9. And this helps me if I want to finish off a trinomial to create a perfect square. So let's go ahead and complete the square for some of these trinomials. So I have x squared plus 4x plus something. Well, I know that my middle term is 4, so if I take 4 and divide that by 2, I know the second term in the binomial is 2. 2 squared is 4, so therefore this number must be 4. And I can repeat this process. So 12 divided by 2 is 6. 6 squared is 36. So x squared plus 12x plus 36 is a perfect square. And I can go a step further to go ahead and factor these. So if I know if the second term is 2, and this is x, so this has to be x plus 2 quantity squared. This is going to be x plus 6 quantity squared. If I do this, now this middle term is negative, so negative 10 divided by 2 is negative 5. So I know my b is going to be negative 5, but negative 5 squared is positive 25. So I know this trinomial factors to x minus 5 squared. And this even works if the b isn't necessarily easily divisible by 2. So negative 5 divided by 2 squared is 25 over 4. And that factors to x, this is minus 5 halves squared. Now if you need to take a moment and convince yourself, go ahead and multiply these out to make sure they go back to these. So why do we call this completing the square? Well, this goes back to geometry, and if your algebra teacher ever showed you algebra tiles, this is pretty much what we're talking about. We can represent values in terms of area. So we can think of 1 as a 1 by 1 square. We can think about x as a rectangle that has area x because it's x by 1. We can think about x squared as an x by x rectangle that has an area of x squared. And so when we write polynomials, we can visually represent them using a combination of these squares and rectangles. Specifically, if we can orient them in such a way that they created a square, we will notice that we can think of it as a perfect square trinomial because its area can be arranged into a perfect square that is x plus 1 by x plus 1, because this is x long and this is 1 long, this is x long and this is 1 long. Okay, so visually speaking, if we distribute this out, this becomes x squared plus 6s plus some number, and we know that it's going to be 9. But we call this completing the square because if we put in x squared and we split the 6 x's on either side, how many units do we need here in order to complete the square? So if this is 3 units long and this is 3 units long, the square that's 3 by 3 is actually 9 units long. And so when we distribute this binomial, that's x plus 3 by x plus 3, we notice that it has an area of x squared plus 6x plus 9. So back to the algebra that we were talking about. How can we take some of these equations and rewrite them to include a trinomial, a perfect square trinomial? Well, first, let's figure out what perfect square trinomial we need. So if we divide 6 by 2, we get 3. And 3 squared is 9. So we know the perfect square trinomial that we really want is x squared plus 6x plus 9. But we don't have plus 9, we have plus 11. In this particular problem is fairly easy to see that we can just split 11 into 9 and 2, and then we can factor this into x plus 3 quantity squared, and then we have the 2 kind of left over. So we've rewritten this into this form, and this form should look fairly familiar to you from the last video. Okay, so let's go ahead and try completing this square. We're going to do the same thing. We know 20 divided by 2 is 10, and 10 squared is 100. So we know we want x squared plus 20x plus 100. But now we run into a problem because we can't split 5 into 100 and something else. So we need a different strategy. If we think back to algebra, when we're solving equations, we have x plus 3 equals 5. And we subtract 3 on both sides. We can do this because when we add 3 and then subtract 3, we get 0. That's the additive property of 0. So if we add a number and its opposite, we're really adding 0. So if I add a number like 100 and then I subtract 100 right away, I really haven't changed the value of anything. And then I add 5. And now I have my perfect square trinomial and two constant terms that I can simplify. So I end up with x plus 10, quantity squared. Negative 100 plus 5 is negative 95. And if I go ahead and expand this back out, it will be an equivalent statement to this. And again, this form should look somewhat familiar to you. Let's try another one. So in this case, I'm going to do something very similar. I'm going to determine what my b should be. So I take negative 7 and divide it by 2. And for this particular one, I'm going to go ahead and just square it as a fraction, so that way I don't have to worry about decimals. So I end up with 49 over 4. So I know I want my trinomial to read as x squared minus 7x plus 49 over 4. But if I add 49 over 4, I also need to subtract 49 over 4. So that way I'm not really changing the value of the function. Don't forget about the plus 6. So now this equation here has the same value as this equation here. So let's simplify. X minus 7 over 2, quantity squared, minus 49 fourths plus 6. So I can change 6 to 24 over 4. So negative 49 over 4 plus 24 over 4 is negative 25 over 4. And there is my completed square. Okay, so if I want to solve equations by completing the square, I can do something very similar. Only this time I have an equation, so I can make my life a little bit easier. I can do x squared plus 20x, and I want to make this a perfect square. So I'm going to go ahead and subtract 5 from both sides, so that way I can figure out what I want here and move what I don't want over to the other side and keep my equations balanced. So again, figure out your b. So 20 divided by 2 is 10. 10 squared is 100. So I need to add 100 to this side. But if I add 100 to one side, I need to add 100 to the other. To simplify negative 5 plus 100, I have 95 equals x squared plus 20x plus 10, or plus 100, factors to x plus 10 squared. Now I have something squared equals 95, so I can take the square root of both sides. So the square root of x plus 10 squared equals the square root of 95. The square root of anything squared is just itself, so I have x plus 10 equals the square root of 95. And if I subtract 10 from both sides, x equals negative 10 plus the square root of 95. You could also have written it as the square root of 95 minus 10, but we tend to get a little messy with our writing, and then you're not sure if the minus 10 should be in the square root or not. And in fact, it should not. We can also go ahead and check to see if 95 can be taken out of the square root. So we start to look for factors of 95. 95 is, of course, 19 times 5, because 100 is 20 times 5. So we notice that we don't have any squared factors in the square root, so this becomes our final answer. Let's try one more. We're going to do something similar, so I want to make room for this to be a perfect square. So x squared minus 7x plus what to be a perfect square equals, if I subtract 6 on both sides, negative 6. Okay, so now I have to figure out what I'm going to add. So I take negative 7 and I divide it by 2. So I get negative 7 over 2. So I'm going to square that. So negative 7 over 2 squared is 49 over 4. So I'm going to add 49 over 4 to both sides. So 49 over 4 plus 49 over 4. Okay, so on the right-hand side, I already have my perfect square. So I can rewrite this as x minus, because remember, b is going to be minus 7 over 2 squared equals negative 6, which I can rewrite in fourths as negative 24 fourths plus 49 fourths. So x minus 7 over 2 squared equals 25 over 4. I can go ahead and take the square root of both sides. So I end up with x minus 7 over 2 equals 5 over 2. Add 7 over 2 to both sides, so add 7 over 2, add 7 over 2, and x equals 12 over 2, or 6. And there's my answer. Okay, so don't worry if you weren't 100% sure what was going on. Completing the square is a very complex concept, so we are going to go over this in more detail once we get to class. Go ahead and complete the 1-2 completing the square reflection. Next up, we're going to watch some conic sections.